Hello class, this is a continuation of a lesson series on solution stoichiometry. In our last lesson, we discussed how to calculate molarity, giving grams and liters of solution. Today we're going to talk about concentration of ions in solution and how to calculate them. We are also going to look at how to manipulate the molarity equation. When an ionic compound dissolves, the solute splits into its respective ions. This is called dissociation. There's another vocabulary word that's very similar, but specifically refers to an acid molecule that dissociates in water. When it does that, it loses an H in the form of H plus or H3O plus. This is called ionization. Whether ionization or dissociation occurs, we can write a chemical equation to represent this. Ionic compounds, such as solid calcium chloride dissociating in water, start off with the solid solute being represented as a single reactant. It then has the reaction arrow, and you see that it splits into its ions, where we have the single atom, its charge, and AQ as our state. This does have to stay balanced and respect the overall number of moles of atoms in particular solution. There is 1 mole of calcium and 2 moles of chlorine for every mole of calcium chloride. Therefore, the coefficient in front of Ca2 plus is a 1, and the coefficient in front of Cl minus is a 2. For an acid example, we have the strong acid sulfuric acid, H2SO4, which ionizes in water. Here, we have H2SO4, which is aqueous, plus water, which is a liquid, and it reacts to form H3O plus aqueous plus the conjugate base HSO4 minus. We'll spend more time talking about conjugate bases and conjugate acids at a later point in time. You can also represent it the same way as we did with our dissociation example above for calcium chloride, where H2SO4 simply splits up into H plus and HSO4 minus. When we're doing calculations for this, we have to multiply the ions by their subscript if asked how many moles of ions are present in solution of known molarity of the whole compound. So let's put that into practice. Give the concentration of each type of ion in the following solution. So a while back, I mentioned that you needed to memorize your polyatomic ions and their charges. In this particular example, we have 0.50 molar concentration for a solution containing cobalt-2 nitrate. Now, the way I figure that out is by looking at the charge in my dissociation equation. So I have CONO3 with a 2 on the outside, and this is going to split up into CO. I'm going to put the charge in a minute, but I'll put aqueous, and then there's 2 on the outside of parentheses, so that becomes my coefficient, and then the NO3 nitrate polyatomic ion has a 1 minus charge. If I have 2 1 minuses, my cobalt must be a 2 plus to balance that out. Remember, an ionic compound has a balance of ionic charges. So 2 plus and 2 negative 1s add up to 0. That is the goal of every ionic compound. Now that I know this, I want to figure out the concentration of each type of ion in solution. So I have the cobalt ion, and I have the nitrate ion. So what I can do is take my 0.50 moles per liter of my original solution and multiply it by the number of moles of ions in that particular formula. I have 1 mole of cobalt-2 plus for every 1 mole of cobalt nitrate, the ionic compound. Just like we saw with some of our other stoichiometry, moles of cobalt nitrate will cancel, and we're left with cobalt 2 plus and liters as our final answer. So in this particular problem, the cobalt 2 plus concentration is going to be the same as the cobalt nitrate concentration. So it is still 0.50 molar CO2 plus. However, with the nitrate ion, it's going to change a little bit. So we're going to set it up the same way. Oops. 0.50 mole of cobalt nitrate over 1 liter. This time you have 2 moles of nitrate ions for every 1 mole of cobalt nitrate. So we have to multiply our answer by 2. When we do this, we end up with 1.0 molar NO3 minus as your concentration, because 0.5 times 2 is equal to 1. Here you see that the units still cancel, moles of cobalt nitrate, and we're left with our moles of nitrate per liter as our unit. Moles per liter, if you remember, is the same thing as M, so that is why I condensed it and made the final unit just capital M. You can still report it this way as well for your final unit, but it's just one extra thing to write. Okay, go ahead and try it on your own. You've got You Try It Set 3, and you have a couple of examples here. Okay, welcome back. We're going to continue today's lesson by looking at how to manipulate the molarity equation. It is a 3-variable equation, so there are a couple of ways to manipulate. Molarity is equal to moles over liters. If I want to get moles by itself, I can multiply both sides of my equation by liters. By doing that, I have canceled out liters on the right side of my equation, and I'm left with moles is equal to the concentration or molarity times the volume in liters. That would give you this equation here. The other way we can figure out, say, the liters, is starting off the same way, multiplying both sides by liters, and then rearranging to solve for liters by itself. If I want liters by itself, I need to divide both sides by the molarity. The molarity on the right side cancels, and I'm left with liters equal to mole divided by molarity. That would be this equation here. Both of those are equations that you should know, or at least be able to derive if you know your original molarity equation. Let's put them into practice. Calculate the number of moles of Cl- ions in a 1.75 liter solution of 1.0 times 10 to the negative third molar zinc chloride. Okay, so I know that I need moles of Cl- ions. If I need moles of a particular amount of ions, I need to know how this thing dissociates. So ZnCl2 will split up into Zn2 plus 2 moles of Cl minus. That will be useful after I find moles of my zinc chloride. I'm given liters and I'm given a concentration, so I have to find moles first. So 1.75 liters times 1.0 times 10 to the negative third molar zinc chloride. And let's do that in the calculator. So 1.0 times 10 to the negative 3, close parentheses, times 1.75. And I get 0.00175 as my number of moles. Now that's my moles for my zinc chloride solution. This specifically asked me for moles of just chlorine ions. So I have to use the same process in the last problem. 0.00175 moles of zinc chloride ions, or zinc chloride, the compound, and I have 2 moles of Cl- for every 1 mole of zinc chloride. Okay, let's check. Moles cancel, moles cancel. I'm left with moles of zinc, or moles of just chloride ions. If I multiply this by 2, I get 0.0035 as my final answer. 0.0035 moles of Cl-. Now I do need to check my significant figures here. I had 3 significant figures in 1.75, but only 2 sig figs in 1.0. Thankfully, 3 and 5 are my only 2 significant figures in my final answer, so I can leave the answer as is. Let's do another one, this time trying to find grams. Here, I'm trying to find grams of barium nitrate needed to make a 2.5 liter solution with a concentration of 1.75 molar. So this is a good question if you're trying to make this particular solution. I need 2.5 liters at the end of the problem, and I need it to be 1.75 molar. How many grams is that? How much do I have to weigh on my scale? This is a really practical problem. 2.5 liters times 1.75 molar barium nitrate . 2.5 times 1.75, and that's 4.375 moles. Now, if I have my moles, I can figure out my grams by converting grams to moles. Now, this work can be implicit, meaning that you set up 2.75 times 1.75 times whatever the molar mass of barium nitrate is. You can do it as one long step, or you can show each part in between, as I'm about to do. So 1 mole of barium nitrate on the bottom, and I need to figure out my molar mass of barium nitrate. So it's occurred to me that I don't have a periodic table open, but I believe that barium has a mass of 137.33. Yes, it does. Okay. So 137.33 plus, there are 2 nitrogens in barium nitrate, so 14.01 times 2, and there are 6 oxygens, so 16 times 6, because 3 times 2 is 6. This gets me a mass of 261.35, and I'm going to multiply that by the 4375 to get my final answer. Okay, so 261.35 grams of barium nitrate. And then if I check my units, moles will cancel here. I also can go back and check that my liters and molarity canceled out to give me just moles. Now, in my original problem, I had 2 sig figs with 2.5 and 3 sig figs with 1.75. So I need 2 sig figs in my final answer. 1, 1, 4, 3 is 4 sig figs. So if I trim that down, I should have 1,100 grams with the particular accuracy that I'm going with. Now, this is not very accurate. If you are using a scale with more sig figs, go ahead and measure 11 or 1,143.406 grams. If you're using a milligram scale, you want to be as accurate as possible with your grams. Then you can say, oh, this is a 2.500 liter solution of 1.750 molar. You just get more sig figs that way. In this particular problem, they didn't give us that many sig figs to start with, so you did need to round for your final answer. All right, go on and do You Try It, set 4. Okay, keeping an eye on time, welcome back. We've got one more exercise to do, particularly looking at the second manipulation, where we are calculating liters from moles and molarity. Here I have a typical blood serum that is 0.14 molar sodium chloride in concentration. What volume of blood contains 100.0 milligrams of NaCl? All right, well, milligrams is not very useful for us, but we know we can convert grams to moles. So first, let's get milligrams into a useful unit. I know that there are 1,000 milligrams per gram of NaCl. Now that I'm in grams of NaCl, I can divide by the molar mass of sodium chloride to get the number of moles. So the molar mass, I believe, is 58.44, but let's double check. 35.45 is the mass of chlorine, plus 22.99 for sodium, 58.44 grams. Okay, 58.44 grams of NaCl per mole of NaCl. Then I know at the end of this problem, my liters is going to be equal to moles divided by the molarity. So let's set this up. I have 100.0 divided by 1,000, which is 0.1, divided by 58.44. I'm not going to round my moles yet, but 0.0017111567 yada 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 is my number of moles here. That is what I'm going to divide by the given molarity in the problem. So I'm going to truncate just to save space. But I'm going to leave the full number in the calculator. I'm going to divide by the molarity of 0.14 and get my final answer. Now, notice our sig figs. We had 4 significant figures to start with my 100.0 milligrams, but we only have 2 significant figures for your molarity of 0.14. So we will need to round our final answer. So let's divide this by 0.14. And we get a concentration of 0.012 liters. Okay. So in this particular solution, 0.012 liters of solution contain 100.0 milligrams of salt. Now, that's kind of hard to interpret because 0.012 liters sounds very small. If we multiply our liters, we multiply our liters by 1,000. Sorry, here. Technical difficulties. Because there are 1,000 milliliters in 1 liter, we see that this is about 12 milliliters of blood. So 12 milliliters of blood has about 100 milligrams of salt. Interesting. 12 ml. It didn't tell you which to report in, so either works, but hey, you can still convert between liters and milliliters if you know that there's 1,000 milliliters per liter. Okay, go ahead and try you try it set 5, and in our next lesson, we'll discuss the dilution formula. Have a great day.